Without objection, the chairman is authorized to declare recess at any time. Before I deliver my opening remarks, I wanted to note that today the committee is meeting virtually. I want to announce a couple of reminders to the members about the conduct of this hearing. First, members should keep their video feed on as long as they are present in the hearing. Members are responsible for their own microphones. Please also keep your microphones muted unless you are speaking. Finally, if members have documents they want to submit for the record, please email them to the committee clerk whose email address was circulated prior to the hearing. Good morning, and thank you to all of our witnesses who are joining us virtually to discuss the importance of scientific computing at the Department of Energy. This hearing is one of a series on research and development activities sponsored by the Department of Energy's Office of Science. Today, we will be examining the current status and needs of DOE's scientific computing programs, as well as the research, development, and workforce training required to ensure that DOE and the nation maintains its leadership in this crucial area. Stewardship of DOE's scientific computing ecosystem is led by the Office of Science's Advanced Scientific Computing Research Program, or OSCAR. OSCAR is also DOE's main sponsor of research in foundational areas such as applied mathematics and computer science. This year, OSCAR was funded at just over $1 billion, about 1/7 of the total Office of Science budget. DOE possesses some of the most powerful supercomputers in existence. It will deploy the nation's first exascale system this year, signaling an exciting new era in the field of scientific computing. Housed at several national laboratories, DOE supercomputers help researchers analyze huge data sets and test complex computational models, greatly accelerating the pace of discovery in the design of life-saving medical treatments, advanced manufacturing, and the prediction of climate systems, among many other fields of research. DOE's supercomputing ecosystem serves as a critical resource for academic and industry users from the US and around the world. I'm looking forward to discussing with our witnesses the real-world applications of these incredible systems and how Congress can ensure that they are continuously maintained and improved. It is also critically important for DOE to support research that will lay the groundwork for future computing capabilities. We are fast approaching the point at which the computing architectures we have relied upon for decades will reach their physical and economic limitations. Therefore, OSCAR must continue to invest in the applied mathematics, computer science, and game-changing technology development activities that will enable powerful new paradigms like quantum computing. As we craft a forward-looking Office of Science authorization bill, I will be looking to our witnesses for insights into how we in Congress can ensure that these activities are robustly supported. As we will explore today, scientific computing holds tremendous promise for accelerating scientific discovery, but we need to use these capabilities responsibly, ethically, and to advance the public good. For example, as computing and artificial intelligence become more powerful, we must ensure that algorithms are designed to protect people's privacy and eradicate bias. We must also stop these tools from fortifying the structures of systematic racism, as we have seen happen with things like predictive policing and facial recognition technology. This will only become more important as DOE's supercomputing capabilities are used to process, analyze, and store sensitive information, such as biomedical data sets. Let's also discuss how to retain a strong role for the public sector here, to fully tap into computing's potential to help solve humanity's most pressing problems, from curing diseases to addressing the climate emergency. And let's involve the public, especially marginalized communities, in shaping the development and aims of new technologies like these, so that all can share in the benefits equally. As you will hear from our witnesses today, we need to pursue an agenda of scientific computing for the people. Finally, as I've said before, research and infrastructure funding represent just one piece of the puzzle. We need a skilled and diverse workforce to maintain the vitality of DOE's scientific computing ecosystem long into the future. I am particularly interested in leveraging programs such as the Computational Science Graduate Fellowship to forge closer connections between the department and minority-serving institutions. We can all agree on the need for greater diversity, equity, and inclusion across our research enterprise. I want to again thank our excellent panel of witnesses assembled today. I look forward to hearing your testimony. Finally, I want to note that it is a busy day on the Hill, and I may have to step out briefly to ask questions on another committee. With that, I now recognize Mr. Weber for an opening statement.
Well, thank you, Mr. Chair, and I'll be glad to, conduct the hearing while you're gone. I do want to thank you for hosting this hearing and to our esteemed witness panel for being here this afternoon, or technically, I guess, this morning. I'm excited to hear about the critical advanced scientific computing research and development activities being carried out through the DOE, Department of Energy's Office of Science. The Advanced Scientific Computing Research Program, OSCAR as you refer to it, is one that enjoys bipartisan support as a priority within the Office of Science. For the past 30 years, researchers within this program have led advances in mathematics and computing that form the foundation for those complex models and simulations. These developments, in turn, have translated to increased knowledge and understanding of everything from bioenergy and climate change to Alzheimer's disease and health models. Today, OSCAR hosts some of the world's most powerful supercomputers and a high-speed network that moves enormous volumes of scientific data at light speed. In the rapidly evolving field of quantum computing and artificial intelligence, OSCAR is dedicated to maintaining U.S. competitiveness and leadership. The program also supports DOE's goal of completing the world's first exascale computing system this year and a second system within the next year. As our competitors race to develop exascale systems on their own, DOE's strong support of advanced computing research within OSCAR is essential to maintaining U.S. leadership in this field. And it's more than just hardware that needs additional focus, I might add. We need significant modifications to today's tools and techniques to deliver on the promise of high-performance computing. Researchers are in need of a new suite of software tools, programming models, and applications to enable effective use of exascale systems. Without software and application R&D, and we'll simply have high-powered machines collecting dust. Additionally, in order to fully and effectively support innovation in next-generation science, DOE must also encourage cross-cutting research initiatives within the department as well as other federal agencies. Within the Office of Science alone, OSCAR resources and capabilities can be used to drive innovation in computational chemistry, nanomaterials for energy applications, improve simulations of fusion energy reactors, and enhance our ability to predict changes in the global climate with next-generation Earth system models. Other federal agencies would also capitalize on these unique world-leading resources. As authorized by the Act of 2020, the Department of Veterans Affairs is partnering with DOE to use high-performance computing in analyzing massive amounts of health data. This data analysis will help the VA better understand diseases and improve veterans' overall quality of life. We should seek to build upon and expand partnerships like this so that the entire federal government benefits from OSCAR tools as well as its technologies. At the end of the day, we're all supporting one thing: U.S. leadership in science, technology, and innovation. There is no federal entity in a better position to lead this change than DOE's Office of Science. That's why I'm pleased that we're very close to finalizing legislation that provides strong support and long-term guidance for the Office of Science. We're making sure that rubber meets the road and that the U.S. research enterprise is well equipped with all available resources to successfully overcome the generational challenges they face. I want to thank my colleagues for the bipartisan outreach and collaboration, and I want to thank the witnesses for offering and bringing their effort, their input. Thank you, Mr. Chairman, and I yield back.
Thank you so much, Mr. Weber. The chair now recognizes the chairwoman of the full committee, Ms. Johnson, for an opening statement.
Thank you very much, Mr. Bowman, for holding this hearing, and Ranking Member Weber. I also want to thank our witnesses for your participation and I have enjoyed reading your thoughtful written testimony. The Department of Energy has long been a leader in advancing new energy technologies, as well as the fundamental and the foundational sciences of physics, chemistry, engineering, and math, and computational science that support energy innovation. High-performance computing, or supercomputing, is one area of the department that has led for decades, and DOE shows no signs of slowing down. The department currently stewards 2 of the top 3 fastest supercomputers in the world. And as we will learn more about from our witnesses here today, the United States is on track to finish building the first exascale computer in the world this year. These systems serve as critical resources for academic and industrial users and are a key component of our economic competitiveness, scientific leadership, and national security. In the past, high-performance computers were needed almost solely for specialized scientific and engineering applications. Now, as we enter the world where thousands of devices all around us are generating millions of bytes of data every minute, high-performance computers can be used to fundamentally improve our quality of life. Public policies play a critical role in supporting the advancement of these capabilities and enabling our society and economy to directly benefit from them. Additional federal investments in high-performance computing will enable the development of new industries, grow our technology economy, and advance our technological leadership internationally. All that said, as we continue to support the development and use of these breakthrough technologies, we must also do everything we can to ensure that we're doing this in a responsible and ethical manner, even in the face of competition from our adversaries. I thank you again for being here, and I look forward to this important discussion today, and I yield back.
Thank you so much for your opening statement, Madam Chairwoman. The chair now recognizes the ranking member of the full committee, Mr. Lucas, for an opening statement.
Thank you, Chairman Bowman, for hosting this hearing, and thank you to all of our witnesses for being with us this afternoon. Earlier this month, the Energy Subcommittee held a hearing on the Department of Energy's Office of Science, which emphasized the essential role of DOE in our federal research enterprise and highlighted our shared support of these programs. Today, we have an opportunity to examine the activities of another Office of Science program in Advanced Scientific Computing Research, or OSCAR. Advanced Computing Research and Infrastructure is the backbone of scientific discovery, not just at the Department of Energy, but at U.S. research institutions nationwide. Through the OSCAR program, DOE supports the development of tools and technologies in high-performance computing, applied mathematics, advanced networks, data analytics, and next-generation computing initiatives. It also hosts some of the most advanced computing resources in the world at its national laboratories. There is a great potential for federal agencies and U.S. industry partners to leverage OSCAR's unique computing resources. With adequate support, DOE's program will revolutionize our relationship with advanced technology and our capacity for scientific progress. This work is vital to our clean energy economy, our national security, and our leadership in science and technology. Yet, we know that our international competitors, like China, are outpacing us in basic research investment and are closing the gap in key computing focus areas like artificial intelligence and quantum sciences. Expanding our capacities in these fields requires a strategic effort with strong federal investment and active public-private partnerships. That's why in this Congress, I've introduced legislation to address those challenges. My bill, the Securing American Leadership in Science and Technology Act, SALSTA, roughly doubles funding for OSCAR over the next 10 years. Another bill I introduced, the Quantum User Expansion for Science and Technology Act, QUEST, establishes a program at the Department of Energy to expand public-private partnerships, quantum resource use, and encourage greater participation in the development of quantum information sciences. Mr. Chairman, at this time, I'd like to ask unanimous consent to submit for the record a letter from the Quantum Industry Coalition on the need to maximize the value of U.S. quantum industry and the role that DOE and its national laboratories can play in this high priority work.
Without objection.
Thank you, Mr. Chairman. I'm also proud to join my colleague and the ranking member of the Investigations and Oversight Subcommittee, Jay Obernolte, on a bill to strengthen the other high priority computing research program carried out at the department. This week, Representative Obernolte introduced the Next Generation Computing Research and Development Act, which authorizes various DOE advanced scientific computer programs. These will support beyond Excel and excellent energy computing, computing workforce development, and applied mathematics and software development activities. This bill, along with the QUEST Act and SALSTA, is an important step forward in improving our nation's global standing in science and technology. We know that maintaining U.S. leadership will require a shared commitment to prioritize DOE and its Office of Science, and nowhere is this clearer than in the advanced computing space. The U.S. relies on computing capacities that only the Department of Energy can provide. We know that the nation who takes the lead in advanced computing will set the stage for the next generation of technologies and technology standards. We cannot afford to fall behind in this race. Last week, I was encouraged by the progress made by our friends in the Senate to recognize the important role the Department of Energy plays in advanced U.S. innovation. But DOE and the national labs shouldn't be an afterthought when we consider the U.S. research enterprise. They're integral to our scientific progress. That's why Chairwoman Johnson and I have been working on bipartisan Office of Science legislation that will make a strong commitment to the Department of Energy and its work, including successful programs like OSCAR. This legislation to support research at the Department of Energy will go hand in glove with the NSF for the Future Act, which supports basic research, STEM education, technology transfer at the National Science Foundation. Together, these research bills will solidify the long-term stability of our international leadership in science. I once again want to thank our witnesses for being here today. I look forward to a productive discussion. Thank you, Chairman Bowen, and I yield back the balance of my time.
Thank you, Mr. Lucas, for your opening statement. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. At this time, I would like to introduce our witnesses. First, Dr. J. Stephen Binkley is the Acting Director and Principal Deputy Director in the Office of Science at the U.S. Department of Energy. Prior to his experience in various leadership positions in DOE, Dr. Binkley has held senior positions at DOE's Sandia National Laboratories and the Department of Homeland Security. He has conducted research in theoretical chemistry, materials science, computer science, applied mathematics, and microelectronics. Next, Dr. Georgia Tourassi is the Director of the National Center for Computational Sciences at the Oak Ridge National Laboratory. She also holds appointments as an adjunct professor of radiology at Duke University and as a professor of the Bredesen Center Data Science Program at the University of Tennessee at Knoxville. Next, Dr. Karen Willcox is Director of the Oden Institute of Computational Engineering and Sciences, Associate Vice President for Research and Professor of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. She holds the W.A. Tex Moncrief Jr. Chair in Simulation-Based Engineering and Sciences and the Peter O'Donnell Jr. Centennial Chair in Computing Systems. Dr. Christopher Monroe is co-founder and chief scientist at IonQ Inc. and the Giloui Family Distinguished Presidential Professor of Electrical and Computer Engineering and Physics at Duke University. He is an atomic physicist and quantum engineer, specializing in the isolation of individual atoms as the core of a quantum computer. Last but certainly not least, Dr. Seny Kamara is an associate professor of computer science at Brown University, where he co-directs Brown's Computing for the People project and the Encrypted Systems Lab. He is also affiliated with Brown's Center for Human Rights and Humanitarian Studies, the Data Science Initiative, and the Policy Lab. Kamara is a principal scientist at MongoDB, a company that provides one of the most widely used platforms to store and process data. Thank you all for joining us today. As our witnesses should know, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you all have completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We will start with Dr. Binkley. Dr. Binkley, please begin.
Okay, thank you, Chairman Bowman and Ranking Member Weber. I'm pleased to come here before you today to discuss the scientific computing capabilities of the Department of Energy, including the forthcoming exascale systems. DOE computing traces its roots back to the Manhattan Project, where extensive use was made of computers. During the 1950s, John von Neumann, a pioneer in computing, advocated for a program that would advance computer development. Over the years, ever more powerful computing capabilities were developed at the national laboratories, beginning with the Lawrence Livermore and Los Alamos national laboratories. DOE and its predecessor agencies have supported applied mathematics and computer science, along with major investments in computer hardware and computational science that have been a major driver of progress in high-performance computing, spurring the U.S. computing industry forward. DOE computing applications have expanded from their original national defense focus to a broad portfolio of scientific research and significant use by industry, beginning with the establishment of the leadership computing facilities at Argonne and Oak Ridge National Laboratories in 2004. Today, DOE computing is a partnership between the National Nuclear Security Administration and the Department's Office of Science. Our two organizations are working hand in hand to advance high-performance computing, including the Exascale Computing Project. The strategic importance of high-performance computing has grown enormously. High-performance computing has become an essential pillar not just of America's national security, but also of our leadership in science. DOE supercomputing has brought major computationally driven advances in a wide range of fields, such as climate science, fusion energy, and high energy and nuclear physics, material science, chemistry, particle accelerator design, and biology, to name a few. Over the last 6 years, we have been very focused on achieving exascale computing. The first exascale computing system is scheduled for delivery at the Oak Ridge National Laboratory to be complete by October of this year. A second system will go to Argonne National Laboratory in 2022, and a third system to Lawrence Livermore National Laboratory in 2023. Exascale has the capability to deepen our understanding of climate change and hasten the development of clean energy. Partnerships between the Office of Science and NNSA with major computing and microelectronic vendors has been key in the development of Exascale. A series of 5 partnership programs have brought DOE-supported researchers to work hand in glove with U.S. high-performance computing vendors, including AMD, Cray, IBM, Intel, NVIDIA, and HPE, to overcome the key technical hurdles in Exascale. In total, DOE has invested $460 million in this effort alone, matched by at least an additional $307 million contributed by industry. Current and planned upgrades to Office of Science scientific user facilities, including light sources, neutron scattering sources, nanoscale and genomic facilities, will bring more sophisticated and precise observations and a vastly larger data outputs. Artificial intelligence and machine learning will play a key role in this. AI also holds the promise of more sophisticated and autonomous facility operations. It has the potential to monitor observations and adjust instrument operations in real time to further enhance efficiency and utilization of the facilities. DOE's ESNet provides ultra-high broadband connectivity across the DOE laboratories. As connectivity will be increasingly vital as facility operations are controlled computationally. We are looking forward and beyond exascale to new frontiers such as quantum information science. Leadership in science remains indispensable to our high performance, or to the country's prosperity, and high performance computing is a key. Continued stewardship and development of the skilled HPC workforce is essential. Our computational science graduate fellowship program is one such activity. Since its establishment in 1991, the program has sponsored over 450 fellows from more than 60 universities. DOE's response to the COVID-19 pandemic demonstrates the enormous value of DOE's high-performance computational resources. In summary, opportunities for accelerated scientific discovery will be enabled by the current era of high-performance computing, marked by the advent of exascale systems and the rapid development of AI and machine learning. And I'll end there.
Thank you so much, Dr. Binkley. Dr. Tourassi, you are now recognized.
Apologies. Chairman Bowman, Ranking Member Weber, Chairwoman Johnson, Ranking Member Lucas, and distinguished members of the committee. Thank you for the opportunity to appear before you today. My name is Georgia Tourassi. I lead the Department of Energy's Oak Ridge Leadership Computing Facility, OLCF, at the Oak Ridge National Laboratory in Tennessee. I'm a biomedical engineer and a computational scientist by education and training. High-performance computing has been the cornerstone for the nation's scientific advancement, technology innovation, competitive advantage, and economic prosperity. Its impact on global competitiveness has long been embodied by the saying, "You must outcompute to outcompete." With advances in data technologies, machine learning, and AI, this saying can be amended to, "You must learn faster to outcompete." OLCF has been a global leader in high-performance computing for nearly 30 years. Currently, OLCF hosts Summit, the nation's most powerful supercomputer for open science. Summit is in high demand for modeling and simulation, data analytics, and AI to better understand climate change, develop new ways to produce clean energy, design advanced materials, advance public health, and overall push the frontiers of science. The request for time on Summit is up to 5 times more than the hours available. Our facility is both deliberate and responsive to national needs. In the past year, I have experienced firsthand our staff's Herculean efforts to pivot fast and offer our world-leading computing resources and computational and data expertise in the fight against the coronavirus. Through the COVID-19 High-Performance Computing Consortium, Summit and our competent staff using world-leading AI helped accelerate discovery, understand the virus, and inform management of the pandemic response. I would like to thank Congress for the CARES Act funds OLCF received to augment Summit and help support the COVID-19 research community. Now, in 2021, OLCF is at the brink of delivering the first exascale computer in the US called Frontier. This supercomputer will perform calculations up to 8 times faster than Summit and will keep the United States at the forefront on high-performance computing. To prepare, the DOE's exascale computing project is developing critical applications across many scientific and technical disciplines to run on Frontier on day 1. In addition, exascale will offer training opportunities to grow a more high-tech and computationally savvy workforce in our nation. It is imperative for the United States to expand and enhance the national research computing ecosystem. DOE has asked us to deliver Frontier 1 year earlier than planned, and we are focusing our efforts on meeting that schedule. Once the system is delivered, we will need to properly fund the operation and applications to solve complex real-world problems in partnership with leading research institutions, industry, and other federal agencies. We need to continuously invest in new technologies, such as AI and accelerated computing methods, to maintain our competitive advantage and ensure our global leadership. We need to make investments in a national data infrastructure that makes the most of our high-performance computing and national data assets. The COVID-19 pandemic demonstrated the value and importance of having established interagency programs and data integration ahead of this unanticipated crisis, and the utility of high-performance computing and AI for rapid, complex, real-world data analysis. The DOE leadership computing facilities are uniquely positioned to support an integrated research infrastructure, combining our leadership computing with national experimental facilities and federal data assets to deliver unprecedented technological, scientific, and economic advantages to the nation. We know high-performance computing is high on other nations' priorities. We know that China, Japan, and the European Union are all investing heavily in exascale computing, and this has implications for both our national security and our overall global competitiveness. We cannot afford to be left behind. Thank you again for the opportunity to testify. I welcome your questions on this important topic.
Thank you so much, Dr. Tourassi. Dr. Willcox, you are now recognized.
Thank you, Chair Bowman, Ranking Member Weber, Chair Johnson, Ranking Member Lucas, and members of the subcommittee. Today I have three main points. First, the future of scientific computing must be interdisciplinary. Second, the DOE ecosystem that supports mission-driven basic research in scientific computing is a national scientific treasure. And third, the future of scientific computing hinges critically on the availability of a highly skilled workforce passionate about addressing the nation's challenges in science, security, and sustainability. So first, on the interdisciplinary future of scientific computing, the pace at which scientific computing can accelerate discovery and innovation will be limited by the rate at which we address foundational challenges that currently limit the complexity, scale, and trustworthiness of computational tools. This requires scientific computing research that draws on many fields, including computer science, computational science, the mathematical sciences, the domain sciences, and engineering. Particularly important is the role of the field of computational science. Computational science differs from computer science because at its core, computational science involves developing mathematical models and simulations rooted in physical and mechanistic principles. As we look to the future of scientific computing, the boundaries between computational science and computer science are becoming increasingly blurred. The future of scientific computing will involve new approaches that span the two fields, such as AI and machine learning. And indeed, the DOE has been at the forefront of defining notions such as AI for science and scientific machine learning. However, when it comes to AI approaches in science and engineering, we must be careful not to chart our course based entirely on the successes of data science and machine learning in vastly different domains such as social media and online retail. We must instead recognize that energy, environmental, and nuclear challenges by their very nature require predictions that go well beyond the available data. There's a critical need to quantify uncertainty and to make informed decisions that account for risk. The future of scientific computing will only address these needs through a balanced investment in the foundational mathematical sciences and in computational science, along with data science and computer science. And we must also not underestimate the criticality of continuing to invest in experimental research and development, since advancing discovery through computational models really requires validation. That brings me to my second point on the value of the DOE's mission-driven basic research ecosystem and its role in addressing these challenges. DOE support for basic research at the national labs and at the nation's universities has fostered interdisciplinary computing research in a way that community-driven basic research has struggled to achieve. And as one example, I highlight the Mathematical Multifaceted Integrated Capabilities Centers, or MIMICs, of the DOE Applied Math program. These centers focus on applied math basic research, but strongly driven by application needs. For example, our Aeolus MIMIC is addressing the basic mathematical research needs for advanced materials and additive manufacturing. The MIMIC program has been transformational in how it has shaped my own basic research portfolio. And what are the critical elements? First, the size of the center is large enough to bring together a diverse team that includes mathematicians, computer scientists, computational scientists, engineers, and domain experts spanning universities and national labs. This in turn enables a much needed holistic approach for a complex system. Second, the long funding horizon provides the stability to invest in challenging, high payoff basic research ideas. And third, the mission-driven nature challenges my mathematical research to target problems that are of high relevance to practitioners. Yet the focus on basic research permits us to lay long-lasting foundations. My final point is that achieving this future vision for scientific computing hinges critically on the availability of a highly skilled workforce. The challenges in front of us are twofold. First is training the workforce with the interdisciplinary skills that cut across the mathematical sciences, computing, and domain sciences. And second is ensuring a strong, diverse pipeline of highly trained professionals who remain committed to scientific and engineering domains rather than being lured away by more lucrative positions in commercial and business sectors. A critical part of this training is the immersive research experiences enabled by basic research grants, such as the MIMIC program I described earlier. Maintaining a strong investment in DOE basic research funding for universities, while also continuing to support the collaborative and academic alliance programs at the national labs, is absolutely critical to addressing the nation's future workforce needs. Thank you, and I look forward to your questions.
Thank you so much, Dr. Willcox. Dr. Monroe, you are now recognized.
Good morning. Thank you, Mr. Chairman, members of the subcommittee for this opportunity to testify before you today. I'm here on behalf of IonQ, a company that builds quantum computers. IonQ is headquartered in College Park, Maryland, and was spun out of the University of Maryland and Duke University about 5 years ago. I'm also a professor of electrical computer engineering and physics at Duke University. I have over 2 decades of experience in the field of quantum computing technology from both academic and industrial perspectives, and I'm here to talk about the future of computing in terms of quantum information. Quantum computers, you may have heard, they're as revolutionary as they are challenging to grasp and build. Their might, given these challenges, demands special attention. As you know, the 2018 National Quantum Initiative, or NQI, was initiated by the House Committee on Science, Space, and Technology to ensure that the U.S. remains at the forefront of this technology. The NQI endowed the Department of Energy, the National Science Foundation, and the National Institute of Standards and Technology with coordination from the Departments of Defense and the intelligence community to stimulate foundational research in quantum computing and other quantum technologies and translate this technology from laboratory to industry. So how does a quantum computer work? It's actually not hard. It's just that quantum computers follow laws of physics that have no analogy in everyday life. So it's confounding. It's not exactly that it's hard. Information in quantum computers can exist in superposition. That is, multiple values can be stored and processed simultaneously in a single memory device. But each time you expand a quantum computer by just a single bit, we call them quantum bits or qubits, its power essentially doubles. So with just 300 quantum bits, that's a pretty small chunk of matter, a quantum computer can process more possibilities than there are atoms in the entire universe. This massive parallelism in quantum computers allows certain computations to be performed that could never be accomplished using regular computers. So a few far-reaching applications for this new mode of computing include optimization of complex problems dealing with huge amounts of data, including logistics and things like pattern recognition. Secondly, molecular and materials design for energy, medical and defense applications. And finally, security, including secure communication, encryption, and decryption or code breaking. IonQ has collaborative projects in all of these areas. And one thing that's interesting in this field is it's such an early stage of this technology that it's...
Time has run out. Can you just finish that last point?
Yes, I think somehow the clock never started.
Yeah,
I
never
noticed.
started, right? That's weird.
I think I was talking for about 2 minutes, but
Yeah, let's put 2 minutes on the clock if we can.
okay, I'll go quickly. So it's critical that quantum computer builders co-design applications with the systems they build. It's really not physics anymore, but all of the physical and chemical sciences, all of the engineering fields, computer science, algorithm design, economics, and even social sciences. So it's no surprise that one of the most important applications in quantum computers is energy, and that the Department of Energy is an important player in advancing this field. So IonQ machines, built and those built by others, are still too small to beat regular computers in these types of problems. But we're at just the beginning of this commercial phase, and the situation will change very soon. The core of a quantum computer is exotic, and its key attribute is isolation. It involves devices either cooled to nearly absolute zero temperature, that's negative 460 degrees, or in the case of our technology at IonQ, we use individual atoms suspended in a small vacuum chamber and poked with laser beams. I should also note that this technology was developed at the National Institute of Standards and Technology in the 90s, where I worked with David Wineland in developing the first quantum logic gate. So exotic as this is, the core technology is not necessarily the main challenge. The real challenge, as I see it, is creating the workforce to understand how to deploy quantum systems. I like to say at the universities, we typically don't build components for people to use, but industry so far has been a little bit slow to develop this technology because they don't have a basis in quantum. And so this is, I think, historically where government laboratories can play a role. At IonQ, our systems are now available on cloud servers. And at Duke University, we're setting up a Duke Quantum Center that will be a scientific user facility that will serve the scientific use cases. And this is very important for the field. I want to conclude. I think it was a lot faster than I thought it would be. But now is a critical time for DOE, NSF, NIST, DOD, and the intelligence community to redouble and coordinate their efforts in translating quantum computers to the real world. One example is the QUEST program that Congressman Lucas mentioned that would subsidize access to industrial quantum computers. Another is endowing the NSF with a technologically driven division and mandate. This is a particularly good way to ensure that this emerging technology gets used in the field. I'm a member of many advisory boards in Europe and in Asia, and I'm well aware of the coordinated investments overseas. The U.S. must lead the race to build quantum computers and other quantum technologies. And I think that the programs and continued stewardship of the National Quantum Initiative by DOE and the other agencies I mentioned are critical to continued leadership. I again thank the committee and chairman for its leadership and for the opportunity to testify today, even though I took, I think, 4 minutes. Thank you.
Thank you, Dr. Monroe. Apologies about the issues with the clock. Dr. Kamara, you are now recognized.
Thank you. Chairman Bowman, Ranking Member Weber, Chairwoman Johnson, Ranking Member Lucas, and distinguished members of the committee. I appreciate the opportunity to testify today's hearing on the future of scientific computing at the Department of Energy. By the end of the year, the Oak Ridge National Lab will receive the world's first exascale supercomputer. This computer will be able to process 10 to the 18, or 1 quintillion operations per second. It is hard to overstate how difficult this is to achieve and what an accomplishment it is. This considerable leap in computing power will open the doors to new discoveries and significantly impact a multitude of fields, including medicine, meteorology, cosmology, and artificial intelligence. It is clear that the world-class research in high-performance computing that has been conducted by U.S. universities, national labs, and industry in order to achieve exascale computing will affect our lives for the foreseeable future. But as we enter the era of exascale computing, I would like to provide a word of caution. I am sure we can all agree that computing and the technologies it enables have had a tremendous impact on society. Because of this, it is easy to assume that technological progress always leads to positive outcomes and that new technologies benefit everyone equally. But this is not the case. Technology, like policy, can have disparate impact. It can enable positive outcomes for some and cause great harms to others. Consider, for example, advances in facial recognition, which allow us to log into our smartphones faster, but also enables suspicionless mass surveillance. Or the progress in computer vision and robotics that enables new drones that can deliver medicine to hard-to-reach rural areas, or missiles at the push of a button by somebody sitting in a room thousands of miles away. We must always remind ourselves that technology is not inherently good and does not always benefit everyone equally by default. In fact, we need to think hard about the harms technology can cause and work even harder to mitigate those harms. One of the many important applications of exascale computing is artificial intelligence and machine learning. For example, to predict how a cancer patient might respond to a particular treatment. But as we know, thanks to the work of scholars like Cathy O'Neill, Joy Bulamwini, and Timneh Gebru, and to outlets like ProPublica, machine learning algorithms can be biased and can exhibit different behaviors on different populations. And as has been widely documented, these biases in machine learning most often harm people of color and those from marginalized communities. So while we should appreciate that thousands of world-class scientists and engineers across the country are diligently working towards making exascale machine learning for cancer a reality, we also have to ask, how many are working on ensuring that these cancer treatment prediction models work for people of all genders and of all races? The investments we are making in exascale computing will improve national security, the US economy, and industry. But will everyone benefit equally from this investment? Will the 13-year-old girl from Washington Heights, New York, benefit from this investment as much as the tech, energy, and pharmaceutical industries? Will there be as much effort to use these supercomputers in the fight against sickle cell anemia as other diseases? Exascale computing is not only an incredible achievement, but it's an incredible resource with the power to shape our lives and those of future generations. As such, we must be careful and thoughtful about how we make use of it. In particular, it is incumbent upon us to make sure that we deploy and use this resource in a manner that is fair and inclusive, that benefits not only the powerful, but those who have historically been marginalized by society and by technology. Thank you, and I look forward to answering your questions.
Thank you, Dr. Kamara. At this point, we will begin our first round of questions. The chairman now recognizes himself for 5 minutes. Dr. Kamara, I'm going to start with you. Thank you so much for your testimony and for your attention to making sure that all people benefit equally from investments in scientific computing and other new technologies. And I understand that you are co-founding a new research institute at Brown University called Computing for the People. Can you talk more about why we should incorporate these kinds of questions into the R&D agenda from the very beginning? What can we do as Congress to design research programs that will prevent harmful applications down the road, keep the needs of marginalized communities and all people in mind, and prepare the computing workforce to engage with these issues as well?
Yes, so as I said in my statement, it's clear that computer science and technology have had a huge impact. But the reality is that as a field, we haven't really centered the problems of marginalized groups. It's just not something that comes naturally to the field. And there's many reasons for that. Some include the lack of diversity in computing, which is something that is well documented. And so there's no natural way for, for computer science research and technology research to really address those problems. And so this is why we're building this institute at Brown. And the motivation is to really make it a priority, right? Understanding the problems that marginalized communities face and how technology can help, and really focusing on that as our main motivation. So that's what we're doing. The way that Congress can help is both in funding this kind of research and in asking questions, right? Making sure that the needs of all people are addressed by technology and by computing research, just as we're doing in this hearing today.
I was muted, sorry about that. How much is a deep dive understanding and analysis of implicit bias in algorithms and computer science a part of this work that you're referring to?
Yeah, it's crucial. So when we design, and I also want to highlight that it's not only at the level of research; it's also at the level of education. So when we teach our students computer science and we teach them how to design algorithms, we're not teaching them how to think about bias and how to address it. We're not teaching them how to think about energy efficiency and how to design algorithms that are not only fast but also that minimize the amount of energy consumption. So these are all things that we want to do in our institute. And basically we want to integrate what we call responsible computing into computer science education and into computer science research as well. And learning how to find biases in data, learning how to find biases in algorithms is a crucial part of that.
Thank you very much. Dr. Tourassi, thanks for your testimony as well. I was intrigued by your suggestion for investing in a national data infrastructure that could be housed at DOE labs and that could play an important role in democratizing AI. Can you say more about what this would look like?
Absolutely. We know that the explosive growth of AI is based on the three pillars: the supercomputing, the algorithms, and data. We talk a lot about investments on the supercomputing side and algorithms, but data is the fuel that will make the engine, the airplane fly. And as I pointed out in my written and oral testimony, the past few years have taught us the importance of having a data infrastructure that makes the most of our federal data assets. Examples with the partnership with the National Cancer Institute, as well as with the Veterans Administration. Building on that thread, because that infrastructure was in place and the interagency partnership was in place with the VA, we were able to pivot fast to address challenges with the COVID-19 pandemic, because the infrastructure was in place to accept data, new data related to COVID-19 cases in the veteran population, to start doing within 48 hours large-scale epidemiological studies and observational studies. So this is what I meant in my statement, that this was an important lesson learned, that we need to be proactive and to put all resources necessary to support that infrastructure. DOE has a long history of building and sustaining successfully data infrastructures and enabling the broader scientific community to make the most of it.
Thank you so much, Dr. Tourassi. I now recognize Mr. Weber for 5 minutes.
Thank you, Chairman. I appreciate that. And I'm going to go back to you, Dr. Tourassi. We're going to keep you on the hot seat for a little longer. First of all, I'd like to congratulate you on all your hard work at Oak Ridge as director of its leadership computing facility. I'm sure you just didn't wake up one day and decide you were going to get into something like that. You've probably been studying it and working at it a long time. And I know I speak for all of us when I say I cannot wait to see Frontier in action this fall. So congratulations. You've noted, Doctor, that Frontier will, on the day of day one of its operation, no less, be ready to run applications across 24 scientific and technical disciplines. Can you take a moment for us not so technical people maybe, to explain why, when it comes to the race to the world's fastest supercomputer, that the hardware development can't be our only focus? Talk to us, please.
Absolutely. As you said, the tool by itself is not the enabler. We need to see the scientific impact. And scientific impact is measured in many different ways. First of all, by the breadth of application domains that benefit by the tool. How much faster we can do scientific discovery across that breadth of applications. And also how efficiently we use the tool. So in partnership with the Exascale Computing project, there is a portfolio of applications that cover many critical mission areas, some of which I highlighted in my report. And we are working very closely with the Exascale Computing team to make sure that the necessary software tools will be in place to enable the scientific community that will need them, as I said, from day one. Some of these applications in climate change, in renewable energy, in advanced manufacturing, in biology and public health, because we know that these are pressing application areas with great societal impact.
Absolutely, thank you. How does the utility or usability of DOE supercomputer, like Summit, for example, compare? This is, we're talking about competitors. How does it compare to some of our competitors' supercomputers?
So clearly, these metrics are not monitored and publicly, known. But we can say for sure for the United States and the leadership computing facilities, not only we are oversubscribed, we operate in the high 90s efficiency. Anecdotally, some of our competitors are certainly behind. So they have the tool, not necessarily the most effective use of the tool. But as I said, this is a race. We cannot just relax in that race. We need to keep moving forward and making sure that we are spearheading this specific domain.
Well, thank you for that. I'm quite sure China has all the information on everybody's capabilities. So we know that. So we do want to keep up with our competitors. We'd love to have that information and point out to us why it really matters. I know the race, we want to be first in the race, but what other examples would you use other than just time and being first? Why does it matter that we get ahead of our competitors? Give us some examples that tie to our country. Can you do that?
Well, certainly the issues of national security are extremely important. And we know that supercomputers have played a very important role in addressing applications in the national security space, and we expect that space to grow even further. As the other panelists and you all mentioned the issues of adversarial use of the technologies we develop. So we need to be very much aware that this is not only present in our horizon, it is present.
Well, perfect. That's kind of where I hoped you would go. I'm going to jump over to you, Mr. Binkley, or Dr. Binkley, I'm sorry. As I mentioned in my opening statement, I believe that in order to fully realize the potential of the world-leading computing capabilities stewarded by our national laboratories, the Office of Science must prioritize expanding OSCAR research partnership with other federal agencies. Very quickly, Department of Energy is positioned to conduct scientific computing research to resolve diverse challenges. How so, in your opinion? I'm going to be over time a little bit.
So we have, in fact, over the last half a dozen years, really put priority on growing the OSCAR program. It was clearly in recognition of the need to develop and then deploy exascale, and as has been elaborated on here in the last 5 or 6 minutes, concurrent with the development of the exascale computer systems has been a very concerted effort to develop applications that are ready, that will be ready on the day the machine is first turned on. The other thing that we've done is we have worked through the National Science and Technology Council processes to coordinate closely with other federal agencies, including the National Science Foundation, NASA, NOAA, et cetera, and have tried to encourage the other agencies to also make investments in the high-performance computing capabilities for their specific applications. And in the case of the National Institutes of Health, as Dr. Tourassi has pointed out, one of the exascale applications is focused on cancer problems stemming from the National Institutes of Health. And I'll stop there.
Well, thank you. I appreciate that. And Mr. Chairman, thank you for the indulgence.
Ms. Bonamici is next.
Thank you so much to Chair Bowman and Ranking Member Weber, and thank you to the witnesses. In the district I represent in Northwest Oregon, researchers at Intel are developing the foundation for exascale computers, commercially viable quantum systems, and also partnering with the Department of Energy to advance other high-performance computing technologies. And I know these efforts will help us transition to a clean energy economy, better predict extreme weather events, strengthen preventative medicine, improve emergency responses, and more. So, Dr. Binkley, it's sometimes challenging to conceptualize the benefits of the Department of Energy's work on scientific computing. I am the co-chair of the House Oceans Caucus, so I especially appreciated your specific example of the work Lawrence Berkeley National Laboratory and Los Alamos and the University of Bristol are doing to provide more accurate pictures of retreating ice sheets contributing to sea level rise. How will future exascale capabilities strengthen our understanding and response to the climate crisis? And how can Congress better support this work through expanding SIDEX partnerships across the DOE?
So let me take your last question first. With the incoming Biden-Harris administration, there has been a reorganization within the Department of Energy that brings the applied energy programs back into the Undersecretary for Science organization. And that gives us very close coupling with the applied energy programs. That is between the Office of Science and the applied energy programs. And I'm hopeful that that will set the stage where we can expand SIDAC to reach the other parts of the department. Going back to the question about climate simulations, our Earth systems model, which has been in development now since about 5 or 6 years, and is slated to be, up and running on the X-scale computer in the fall, we are systematically increasing the resolution of that model by use of the power of the X-scale computers to have higher resolution, more predictive models of climate effects, and then we'll be able to predict areas that are going to be problematic in the future. That'll become, I think, a fairly standard tool for predictive Earth systems modeling. I'll stop there. You're muted.
Sorry about that. Dr. Binkley, thank you. I do want to get in another question. Dr. Kamara, we know that technology is not developed or used in a vacuum. A growing body of evidence suggests that left unchecked, digital tools can absorb and replicate systemic biases that are ingrained in the environment in which they are designed. For example, one hiring algorithm, often referenced for its apparent biases, identified high performers as anyone named Jared who played lacrosse, even though those features had no connection for the actual job for which the firm was screening. And unfortunately, digital tools are opaque in their design and operation, and it's hard to hold them accountable. So what steps can Congress take to prevent harmful bias in the research, development, and commercialization of supercomputing technologies? And will advances in neuromorphic computing help to end or minimize bias, or simply make it harder to detect?
Yeah, so there are a lot of ways that bias can creep into algorithms, and there's a lot of research going on how to mitigate that. So a lot of people are thinking hard about that, and that's great. But what we also have to be careful of is that just because we can automate something doesn't mean that we should, right? So it's not enough to just say, okay, well, let's design unbiased algorithms. We can make some effort, towards that. But we also have to ask ourselves, should we be using algorithms, in these particular cases, right? So should we be using algorithms for estimating the probability that somebody is going to commit a crime? Is that the right use of this technology? Okay, so there's a lot of different sort of aspects of this that we have to think about. And the way Congress can help is in funding more research on fair algorithms and also on providing some infrastructure for auditing algorithms. That is also an important component of this, is that we need to be able to say, okay, well, if an algorithm is going to be deployed, right? If we are going to make the decision to deploy some kind of algorithm in a particular use case, then we really should have rules in place for how we're going to audit those algorithms, how we're going to make sure that they don't discriminate and that they're not biased.
Right. And your thoughts on neuromorphic computing and what that means to bias and minimizing bias?
Well, that's a little bit outside of my of my scope of expertise, but I would definitely say that these different types of sort of as we diversify the kinds of algorithms that we're using, it's going to be harder and harder to detect bias, right? So we also have to really be really mindful of this. It's easy to think that, well, just because an algorithm is running or some kind of algorithm, and there's many different types, that there's sort of this veneer of objectivity, but this really isn't the case, right? And so we have to be really vigilant against that.
Thank you, Mr. Chairman. I yield back.
Mr. Baird is next.
Thank you, Mr. Chairman, and thank you, Ranking Member Weber, for holding this session. It's very interesting and exciting to me. Of course, my background is agriculture, and so I'm going to relate agriculture to this quantum computing. I recently introduced a bill, 2961, that really says that the Department of Energy Biological Innovation Opportunities Act, and that's making sure that DOE has sufficient infrastructure to be able to provide access to quantum computing to researchers and university people, as well as the industry. So I was trying to mention that because it'll be a part of Ranking Member Lucas's SOLSTA bill and keeping us in the leadership around the world. But Dr. Monroe, you noted in your written testimony that translating quantum computing to practical applications will create opportunities for the workforce. I would also suggest that it will provide students and researchers the ability to analyze large-scale, complex practical situations. And an example of this is the National Institute of Food and Agriculture's Genome to Phenome initiative. It's designed to look at plant materials and give plant researchers the ability to analyze those plants and look for the visual characteristics and tie that to the genome. And that all is designed to improve our ability to raise food and feed a hungry world in the future. So, Dr. Monroe, would you care to elaborate? You were talking about practical applications and the need for that. Would you care to elaborate on what quantum computing can do for us in agriculture and how you think that fits into the progress of our world?
Yes, thank you for the question. So yeah, sorry for my garbled statement. I think I had to kind of jump around a little bit on the hot seat there. So quantum computers appear to be good at solving generic optimization problems. That is, problems that have way too many inputs that we can't sample all of the configurations on a conventional computer. Those are called combinatorial optimization problems, and we take guesses with even high performance computers. And as I hinted, there are problems out there that we'll never be able to solve because the number of configurations is just way too big. And so you mentioned agriculture, but I would maybe broaden it to pharmaceutical, energy, and gas and oil industry. The need to understand the structure of molecules. This is something computers are also very poor at, because even a small molecule, if it has more than a few hundred electrons, and this is even the caffeine molecule has 100 electrons, we can't easily model that molecule to see how it interacts with others to form catalyzers, better fuels, to form better drugs even. But at the same time, there's a logistics problem. Even in big pharma, if you have 10,000 compounds, which combination of 10 of them make a good drug for something? We may have models of that, but once again, we can't optimize that. And on material science side, and this is closely related to what you mentioned in plant science and agriculture, can we develop new materials that harvest sunlight much more efficiently than known materials today? It's this for the same reason. We can't compute or simulate the behavior of these very fundamental things. So, quantum computing is just starting, but those are the types of problems that are naturally attackable by a quantum computer. And I'll put it this way: those problems will never be solved using conventional computers. If they are to be solved, they will demand a quantum computer. So it is a very researchy field now, but we're starting to launch into building devices. And the Department of Energy, over the last half dozen years, has played a big role in their laboratories in trying to translate that research, basic research, to product. And I think industry is starting to play a role as well. Very big named industries that you've heard of.
You're exactly right. This genome to phenome, they're taking spray rigs that are 60 foot wide with cameras down to look at each and every plant. And there's no way in my background in the past that we could have had the ability to analyze that much data. So thank you for that. And I see I've got about 13 seconds left, and I have other questions I would like to ask the other witnesses, but I thank all of them for being here and appreciate this opportunity, and I yield back.
Mr. McNerney is next.
Well, first of all, I want to thank the witnesses. It's great to hear your viewpoints and to share the excitement about what's going on with these exascale computers. Dr. Monroe, you mentioned some of the potential applications, including pattern recognition, huge data sets, molecular and material design, and secure communications. The DOE and several other agencies are engaged in the National Quantum Initiative, which was authorized by Congress in December 2018. This initiative includes basic research activities and establishes a large-scale quantum information science research centers. How have these activities in the DOE research ecosystem in general helped strengthen the nation's quantum computing industry?
Thanks for the question. Indeed, I think DOE has shown in force their establishment of 5 very highly scoped centers distributed throughout the country that each have a separate mission and aim in the general field of quantum information, not just quantum computing, but quantum sensing, things like quantum simulation. And these, I think the DOE laboratories are a great place to think about this, because the DOE labs, in a sense, are that ideal combination of having seasoned engineers, device people, but also not being a stranger to the weird laws of quantum physics that underlie these devices. So things are just getting started. I as a disclaimer, I am a key contributor to a DOE quantum center headquartered at Lawrence Berkeley National Laboratories in your state, and it's a very exciting collaboration that our consortium will build systems, and we're interested in sort of the system engineering of when you build a big system, it's a sort of a breathing thing that's not just the sum of the individual parts. And with the DOE laboratory at LBNL and also Sandia National Laboratory, New Mexico is involved. We hope to really further the field. But I should also mention the National Science Foundation and NIST are big players. They've historically been at the field since the beginning in quantum, and they one beauty of our national system in funding science is that we have many agencies, all with different missions. DOE, obviously, I think the centerpiece are the laboratories. NSF, they're more vertically organized in a certain sense. They can bring together physicists with computer scientists and everything in between to come to bear on this. So I think collaboration between those agencies is really what's going to keep the American in the lead in this field.
Excellent. Dr. Binkley, you first discussed the importance of strengthening the core research that feeds into technologies like quantum sensors and networks. Would you discuss that a little bit, please?
Yes. One of the major premises of the DOE activities in quantum information science is to be really focused on the fundamental science first, and then follow that through with technology developments to get practical applications. And so if you look across the Office of Science portfolio of activities, it's chemical and material sciences. Well, those are systems that are governed by the laws of quantum mechanics. It's nuclear physics and high energy physics, governed by the laws of the Standard Model. And essentially, quantum mechanics permeates through all of the physical sciences activities that are supported by the Office of Science. And, that is, I think, the major focus of how we're organizing our QIS activities.
Well, thank you. Moving on, Dr. Monroe, in your written testimony, you note the proposed Quest program. How much annual funding is needed for this program? Do you think it would make sense to ramp up the program from a relatively smaller amount over the first few years?
I think there's some amount of sense there. I think quantum computing systems that are capable, that itself is ramping up right now. I think things started maybe 4 or 5 years ago, very small systems. And these are provided by companies you've heard of. Some maybe you haven't, like my company IonQ, but also Google, IBM, other companies are putting these devices out there. They're very expensive, and I speak from experience that industry, the bet that quantum computing will have a commercial payoff, it's going to be a long-term bet, and it's not easy for companies to play that risk. And I think this will allow the Department of Energy and the U.S. government to help connect these systems to users, and help subsidize the use of those machines. And I'll also say, and one thing that the wild card to me is that the killer application for quantum computing, I'm not sure when it happens. I can't predict what it will be, but I'm pretty sure that it will happen out of left field from somebody that thought of a problem that I don't know about, or none of us makers know about. And getting them connected to the system will just hasten progress in the field, because as soon as we hit that killer application, I think it's just going to explode. So you're mentioning of ramping up the access program. I certainly think that's maybe not a bad play, but I think it needs to get going. We need more industrial involvement in this field, less risk. Thank you.
Well, I've run over my time, so I'm going to yield back at this point.
Ranking Member Lucas is next.
Thank you. As I've made clear, I believe that ensuring strong support for the Department of Energy and its world-leading national lab system is essential for our global leadership in science and technology. And this is one of my highest priorities as ranking member of the Science Committee. So I asked my first question to Dr. Monroe, and I'd like the rest of the panel's comments too. And bear in mind that part of our responsibility as ranking member and my colleague as chairman of this committee is not only to try and create the right policy here in the Science Committee, but also we have to be able to persuade our colleagues in the body as a whole, and ultimately the American taxpayers, that we are on the right track. So I asked the following question in that vein. In your respective areas of expertise, what would it mean to U.S. leadership in advanced scientific computing if we fail to provide adequate support for DOE Office of Science? Start with you, Dr. Monroe, and whoever in the panel would care to touch on that.
Sure.
This is a message for my colleagues who may not be spending time listening to this committee hearing, which flabbergasted me, I acknowledge.
Sure. I'll answer very briefly in my own field of quantum computing that, again, we're at the early stages of this field, and it is absolutely critical that industry eventually take it over. And I think the DOE labs in particular, but also university laboratories supported by NSF and NIST under the NQI, it's essential that they are able to make the investments necessary to keep the U.S. ahead of the world in this field. We're ahead now. We have mighty industry just waiting in the wings to take it over. We have to translate it. It's absolutely critical given the coordinated investments from folks around the world.
Anyone else care to take a stab?
So I could go next. Certainly, if we stop the investments, essentially we are going to stagnate scientific innovation. We will stop innovating, not only across basic sciences, but also across applied sciences. Since we're using quantum computing as an example, as Dr. Monroe said, this is the beginning of a promising and disruptive technology, but it will take more than a decade for that technology to become reality for all of us. What happens in between? And it is classical computing that will lead to those innovations of materials, new materials that are needed to advance quantum computing. So it is a relay, and we cannot just pause and wait for the next big thing to come out from another nation.
I could go next. There's another dimension to this that I think is really important to keep in mind, and that is that to be first in innovation, to be first in economic security and so on, national security, it's really a race for getting the best and brightest people into the United States to do new research in areas like quantum information science that have not been a topic of heavy investment before. It's essentially the best tools attract the best people. And that works in our advantage in an international context. And so having, the best workforce ultimately is something that we need to strive for.
I'd echo Dr. Tourassi's comments and to say that underinvestment in the Office of Science would absolutely stagnate and in fact set back our ability to tackle the critical challenges in energy, security and environment particularly, and the nation and the world just can't afford that.
With that, I thank you. You make very compelling cases. My time is winding down. I would observe one other thing. We are very sensitive in Congress these days about not only international competition, but how we protect U.S. research from theft. At the same time, encouraging transparency and a cooperative environment. Anyone in a few seconds who'd like to touch on that, I'm more than pleased to hear what you have to say. But that's the struggle we're also facing, how to give you the tools, create the environment, but at the same time, preserve your good work and the work being supported by the American taxpayers.
Well, I would add, Congressman Lucas, that's something that we are really focused on. In fact, the meeting I was in just prior to this hearing was a National Science and Technology Council meeting focused on research security. And I can attest to the fact that a number of, in fact, all of the major science funding agencies of the federal government are really focused on this problem these days. And it's a very difficult problem. We're trying to develop policies that will protect the U.S. interests. It's a very thorny issue. And in the Department of Energy, we've already, because we have such a large research establishment in our national labs, we have over the last 3 or 4 years begun implementation of policies to help protect the results of research from being, taken illicitly.
Thank you, Doctor, and thank you to the entire panel. My time's expired. I yield back, Mr. Chairman.
Ms. Stevens is next.
Great. Thank you so much, Congresswoman Haley Stevens from Southeastern Michigan, and a major fan of supercomputers and supercomputer technology. And today's hearing, I couldn't be more grateful. In particular, I've had the privilege of working on a supercomputer program called the National Digital Engineering Manufacturing Consortium, working in partnership as a public-private partnership between Purdue, OSU, and a handful of small businesses in the Great Lakes area, funded through the Economic Development Administration. Also, I think I'm getting some feedback, Weber. That might be you. I think I'm getting Weber to chat, which I love hearing, but I want to brag
Weber,
about the
please,
endemic program.
mute your mic.
Now back to financial services.
Okay, great. Thanks. Thank you, Mr. Chair. Thanks. So we got this endemic program. We saw it. Jayco Plastics was able to develop a new product line, resulting in 100 new jobs. And Dr. Tourassi, first of all, it's always a privilege to have somebody from Oak Ridge at a science hearing. And we have a tremendous amount of respect for your capabilities and partnerships out of Oak Ridge and all that you have represented. And your hearing touched a little bit on this, but I was just wondering if you could shed some additional light. And this could also be open to anybody, but I'm just feeling like Oak Ridge might have some insight into this with supercomputer technologies, public-private partnerships, and also abilities to lead to the creation of jobs, either at small enterprises or large, and what else we could be doing in Congress to advance these opportunities.
So as you know, building the supercomputers represent a strong partnership with our vendors. And from that point on, it's what kind of science we enable, right? These are the scientific innovations that will lead to technology transfer and they will lead to also job growth opportunities. We talk a lot about artificial intelligence these days and about what artificial intelligence will do to our workforce, both positive and negative effects. And certainly, when I'm an optimist and a proponent of developing, and as I said, a computationally savvy, aware, and ready workforce. And I see the role of the leadership computing facilities being pivotal in that space as well. It is not only how to use the computers, it is not only how to do the science, but how exactly we develop a workforce that can support the data infrastructure that we mentioned earlier. And that is a different flavor of data, of a workforce that is absolutely needed for our nation. So I would encourage all of you to keep thinking along those lines as well. It takes a lot of effort to collect, curate, and manage data. These are technical expertise right now that we don't have enough in the nation. So we should be building that workforce and create opportunities for smaller companies to play a role in that.
Yeah, and we could go on here too, because part of why we had this endemic program, the National Digital Engineering Manufacturing Consortium, was particularly because of costs. And that was about 10 years ago now. So I don't know if any of our other panelists, while I have about a minute left, could shed some light on, in addition to Dr. Tourassi's really great statements around workforce and some of the barriers to entry because of workforce and human capital, but any barriers to entry that we need to be considering for small to mid-sized enterprises with supercomputer technology and costs in the year 2021. I don't know if Dr. Willcox or Dr. Monroe have any insights into that. Go ahead, Dr. Monroe.
Go ahead, Dr. Monroe.
Okay, yes.
You unmuted first.
Okay. Thank you for the question. Indeed, so IonQ is a sub 100 person company, notably about to go public in the next month. And of course, we're still building machines and looking for use cases. And as a small company, I think while this hearing is predominantly about high performance conventional computing, as it turns out, I think it was mentioned that you do need high performance computers to not only optimize and run, but use quantum computers. They have to be developed in parallel. And this is why actually we do have a relationship with Oak Ridge, a working relationship where they can run small algorithms on our machines, and we in exchange can maybe use some of the advanced computing machinery located in Tennessee. So indeed, it's important. These are capital intensive purchases to be able to have your own array of GPUs on your own site. We don't have to do that all the time, but it's very important in my own field that we're able to get access to very high performance computing machines, and we do rely on DOE for some of that.
Right. You're relying on DOE and our labs and maybe universities. Well, I'm out of time, but this was great. Thank you, Mr. Chair. Great hearing. I yield back.
Forgive me, Ms. Stevens. Mr. Feenstra is next.
Thank you. Thank you, Chairman Bowman and Ranking Member Weber. I want to thank each of the witnesses for their testimony and sharing their extensive research and experience. It is truly outstanding, all the leaps that we're getting into and the cutting edge of this technology. I want to direct this question to Dr. Tourassi, and thank you for being here. I mean, it's just a pleasure to see you. Accurate weather forecasting is incredibly important in my district, not only for the farmers in Iowa as they predict the growing seasons and the harvest, but also for covering severe weather events for the public. Dr. Tourassi, in your testimony, you highlighted the use of Summit to achieve a milestone in global weather forecasting simulations. Can you elaborate on the milestone and how it will help in the future weather forecasting, and how the advent of exascale supercomputing will also be able to build on this?
Absolutely. And this is something that Dr. Binkley addressed earlier on. simulating, modeling climate and weather forecasting is one of the most complicated problems because we deal with many different physical systems interacting with each other. So, and this is something very similar that happens with the biomedical and the biological space. If you try to understand only one dimension of the problem, you just miss the big picture. This is what high-performance computing and supercomputing has done throughout the years because it enables modeling and simulation and weather forecasting by increasing the complexity of the components we add in the equation. We can take into account atmospheric patterns, we can take into account soil information or ocean information. And that's how these models, with the support of Summit and in the future with Frontier, will provide models that are more detailed and they are more precise. Now, of course, it's an oxymoron in some ways to say we will do weather forecasting in the most precise way because the atmospheric system itself is a chaotic system. Still, though, we are decreasing the uncertainty according to which we do these predictions. The way the community has been moving, and again, I'm speaking a little bit at the high level because I'm a biomedical scientist, we know that when you're dealing with a problem that is very difficult to predict, effectively you try to create a number of models and just throw them in parallel and see what they do. Think of it as an ensemble approach. And then we aggregate the results of these models. As the supercomputers are getting bigger and bigger, what are we able to do? First of all, run more complex models. Second, run more of them, therefore increasing the precision of our predictions. And this is what we're experiencing with Summit, and this is what we will see with Frontier even more.
Wow, thank you so much for that answer. I've got one more question. I quickly, Dr. Binkley, as part of the Argonne's early science program, a team from Iowa State and Ames Lab is rewriting software program called IonQ for the exascale era. The new program could provide an increase in the size of chemical systems that can develop new methods for converting biomass into biofuels. This could be groundbreaking. Can you talk about how exascale computers can be used for breakthroughs, such as in the many different areas, including biofuels?
Well, certainly the example that you're citing, the EnWChem, which is one of the foremost quantum chemistry codes, it's been around for a number of years, and it was developed originally at the Pacific Northwest National Laboratory. And, making an effort to bring that software set into operation on the exascale computers is a major step. And it's something that our basic energy sciences program has been supporting. There are a number of other codes that I think are going to have transformational effects. There are fusion simulation models that are under development for use on the exascale computers. There's also software for understanding seismic events. If you look at the list of the 24 exascale applications that are slated for first use, a number of them I think are poised to have breakthroughs.
Yep. Yeah. Yep. Well, thank you so much. And my time is up. Thanks everyone for being on the panel. This is great information. I yield back.
Mr. Caston is next.
Thank you so much. I really appreciate our witnesses being here. And have some questions for you, Mr. Monroe. My district is just north of Argonne National Lab and just to the east of Fermi, which means I can't claim any, but spend a lot of time at both. And of course, that's where a lot of the really groundbreaking deployment of quantum computing is happening. I want to first just be a little bit nerdy with you. When you were listing some of the types of questions that you can uniquely answer with quantum computing, I think you mentioned optimization problems, encryption, decryption, some issues around protein chemistry, all of these sort of classes, sort of NP hard problems where the solution space is huge and you can just jam through a lot of data. as you look at sort of the opportunities, is it uniquely to those classes of problems that just you can churn through a lot more data fields a lot more quickly, or are there other classes of problems that you're also excited about?
Maybe I'll answer it in two ways. Thanks for the question. Always glad to put the nerd hat on. So the one disclaimer I'll say is that it's very hard. It's very hard to prove that a quantum computer can find the absolute optimal configuration of variables in some complex model. However, it could be a heuristic, meaning that it could do better than any conventional computer. You don't really need proof. All you need to do is show, well, it gave me a better answer. It gave me a shorter path of some route subject to certain constraints. You don't need to prove it. And that's sort of why quantum computers have to be deployed. We need to build them and deploy them as soon as possible and sort of see how well they perform. The other way I might answer this question, this might be too universal, is that I think every application in a quantum computer can be cast in terms of an optimizer. Optimization is a very general thing. Even code breaking application, which is actually factoring numbers into their primes, that's a very hard problem. It's easy to multiply. It's hard to do the inverse, to factor. You can cast that in terms of an optimization problem. It's optimizing the two numbers that actually multiply to give the original number, and that has revolutionary impacts on security. But one thing I want to conclude here with is you shouldn't think. I hesitate to describe quantum computers as big data machines. They don't process big data in a way that you can get access to all the big data. You can't compute massive parallel. You can't model every molecule in the atmosphere and predict exactly what the weather's going to be. You need problems that sort of have a very small, a very simple answer at the end. Like, there's a model of climate I have in the upper atmosphere. I don't know how to solve it. I don't know what conditions will validate this model. It's those problems that quantum computers can do. They sample lots of data, but you only get there's like a winnowing down to getting only a very small amount of information at the end. So it's a little bit subtle. And so high performance computers are one-to-one machines. They can compute brute force, function evaluation with all these inputs and all these outputs. Quantum computers do something a little differently.
That's fascinating. I'd love to follow up on that with more time than we have, but let me leave with a question to you, but invite all of our witnesses to respond if you have thoughts. When I've gone down and toured these facilities at our labs, I'm always struck by the fact that part of the excitement is these NP hard, huge data set problems for all classes of supercomputing. And then the other conversation we always end up getting into is the ethical questions around what does it mean to have a computer that's capable of asking questions that our brains aren't capable of thinking of, and what's the appropriate boundaries there? And I'd welcome any of your thoughts on what we should be doing as a legislative body to, and maybe we're doing enough already, to put those ethical boundaries in place and really understand how do we make sure that that we don't hit whatever that moment was in Terminator, where the computers are smarter than we are and we can't figure out why.
Well, I'll answer very briefly there and leave it to the other witnesses. This is a little bit passive, but I think I think there's an impetus for us to get there, no matter what. Because if we don't understand some revolutionary form of computing and we don't get there, others will. And so I think that that's some type of ethics. At least we're at the forefront of that new technology. I agree with you. It can be vexing when you get a new technology, how to use it ethically and so forth. But it's very important to get there and not just ignore it and decide not to get there. And if we do that, others will.
Well, thank you. I'm out of time. Would welcome any thoughts that the rest of the panelists have in writing afterwards. Thank you. I yield back.
Mr. Obenoti is next.
Thank you very much, Mr. Chairman, and thank you to our witnesses for a fascinating hearing. And also thank you for allowing me to participate. I know I'm not a regular member of the subcommittee, but this is a subject that I find extremely interesting. I think it's important to recognize that just how much this concept of beyond exascale computing has the potential to change computer science and its contribution to humanity in general. I mean, when we're talking about computers that can actually perform more calculations per second than the human brain can, we can approach these artificial intelligence problems in ways that that we just hadn't been able to in the past. So it's a very exciting thing to be part of. Certainly something that we need, as a federal government, need to be stimulating investment and research into. So a question for Dr. Binkley. When you were talking about in your testimony about beyond exascale computing, you mentioned that quantum computing is probably going to be the lead in that. And my question to you is do you think that quantum computing is the only technology that's capable of beyond exascale power, or are there other technologies, traditional technologies, that might also be capable of that?
Well, I don't think that quantum computing is going to lead to the elimination of the type of computing that can be achieved on current supercomputers, including exascale. I mean, as Chris Monroe has pointed out, quantum computers are very specialized in the type of calculations that they can do. Conventional computers, including exascale, use numerical methods and follow principles of sort of orderly input and orderly output. And so I think that what is going to come next after exascale, if you look at the typical exascale computer, each node in the computer has both a conventional CPU chip and some type of graphical processor. And it's the combination of those two that allows one to attain 10 to the 18 floating point operations per second. Experiments are beginning now to look at other types of computing elements that could be included into a supercomputer. And so other types of GPUs, one could imagine neuromorphic chips that could be incorporated. I think there's a lot of research that can be done in those areas. And I think that the lineage that has led us up to exascale still has more steps to go through as we go forward.
Well, thank you, Dr. Binkley. It's as a computer scientist myself, I find this extremely interesting and really inspirational. And before I go, if I could just make everyone aware of a piece of legislation that I've introduced. It's HR 3284 that would direct the Department of Energy to establish a program for capabilities beyond exascale. And one thing that I think we need to do more talking about is the need to research energy efficient computing, because if you look at the current generation of exaflop capable supercomputers, one thing that strikes me is the pure amount of power that they consume. I mean, the El Capitan supercomputer that's being installed at Lawrence Livermore Laboratories, I believe, is going to have a power consumption on the order of 40 megawatts. So, the amount of energy they consume and the heat that they consume is going to quickly become a barrier to our ability to employ these kinds of technologies. So as part of this bill, I'm suggesting that we also establish a program to stimulate research into energy efficient computing. And then, of course, I know in the testimony was mentioned support for the Computational Science Graduate Fellowship Program. That's a program that I am very supportive of. I think that at the same time that we are stimulating research into these technologies, we also need to make sure that our academic population and our workforce is prepared to employ these technologies. It's going to be no good to make the tools if we're not also stimulating the kind of workforce that's going to be able to help us take that to the next level. And this bill would also do that. So I would certainly invite everyone's support and participation on that bill. And I'll yield back, Mr. Chair, but thank you very much for letting me be part of this discussion.
Mr. Lamb is next.
Thank you, Mr. Chairman, and I apologize up front if I have any internet connection problems here. It hasn't been the best day for me on that. The first thing that I wanted to ask was for Mr. Monroe. There's a statement on the Department of Energy's website that says that right now we're at the same point in quantum computing that scientists in the 1950s were with computers. Do you consider that an accurate statement as far as kind of placing in context where we might be in the development of quantum computing?
Yes, thanks for the question. It's a interesting comparison, and I buy into that with the caveat that we're sort of on this exponential curve in progress. And so, 10 years back in the 50s is maybe like 2 years now. So, all of us students of history, it's wonderful to see the progression from vacuum tubes to germanium transistors to silicon, and then silicon. We built silicon out. It took 20 or 30 years for that to happen. We don't expect that to be the same with quantum. I think we are on the cusp of several different technologies, superconducting circuits. At IonQ, we work with individual atoms. We know how to scale these things. We have to put the engineering effort into it. So the comparison is a very good one because we're at very low levels now. We don't have windows for quantum yet. We're working with individual gates, very low level stuff that they were doing in the 50s with silicon transistors. But we also know that software exists for classical computers, conventional computers, that we can also deploy and accelerate in quantum. So yes, it's 1950s in quantum, but we're sort of moving much faster.
Good, thank you. And you put in your testimony that you thought the Endless Frontiers Act would be helpful to our efforts to go even further in quantum computing. Could you maybe just say a little bit more concretely why that is? Because I'm a supporter of that bill. I think it's incredibly important. I do think there is some hesitation for those familiar with the NSF that it could somehow maybe detract from the core basic science mission of the NSF. So would you be able to address that and assuage those concerns?
Yeah, my understanding is there are many different approaches to retasking the NSF to have a technology edge to them. My understanding is also it's not a zero-sum game, that the NSF will still have in its core mission the ability to do research, blue skies research for research's sake. I want to link that to technology, especially quantum technology, and why NSF is very well suited to play a big role in the development of the tech, not just the science. And that is the future of quantum computing. We need applications, and right now they're coming in the name of science, mainly in universities. At Duke, in the University of Maryland, we're deploying our laboratory systems to do models of black holes and wormholes, believe it or not, things that maybe a company would never do. And it's those scientific applications that are happening right now. They're also happening at Department of Energy laboratories across the country. Companies won't pay for this. They're not going to build a device to do black holes. So having an agency like the NSF that has an eye on the blue skies, fundamental science research, building and using quantum computers, making a user facility, for instance, is a really good idea because it's going to tide us over until industry really controls the building of these devices. And then we can use those devices for new science, just like we're using exascale and high performance computers at Oak Ridge and other DOE labs for current science.
I agree. Thank you. I do want to just sneak in one more question. Dr. Tourassi, thank you for everything you're doing. Very excited for the launch of Frontier this year. Is there, in somewhat simple layman's terms, a way to describe a problem that we cannot solve until we get Frontier? I understand that it'll probably solve other problems faster. Are there new actual types of problems that this platform will allow us to solve that we couldn't before?
That's a good question. Actually, what we are hoping that the next machines will enable is that pure integration of modeling and simulation with large-scale AI, bringing together models and observational data that we can get from our different experimental facilities and from the rest, let's say in the biomedical space, from the different federal agencies. That level of computing has not happened yet. It goes back to the example that was given earlier about the Phenome-Genome Association studies, which actually are a very challenging and attractive problem for exascale computing when we're looking at large populations of let's say, humans when we want to do at the population level phenome-genome association studies, which will drive new treatments, personalized treatments, precision medicine.
Great, thank you. I'm out of time. Mr. Chairman, I yield back.
Ms. Ross is next.
Thank you, Mr. Chairman, and thank you for holding this hearing, and to all the panelists for joining us today. The committee members have heard this before, but to the panelists, I represent the Research Triangle area of North Carolina. I represent Wake County, and the Research Triangle area has a growing ecosystem of hundreds of innovative and collaborative companies, including science and technology firms, government agencies, academic institutions, including Duke, startups, and nonprofits. The IBM Quantum Hub at NC State University is a cross-disciplinary center of quantum computing education, research, development, and implementation. The IBM Quantum Hub at NC State works with researchers from Duke and UNC Chapel Hill to help partners develop quantum teams and explore promising use cases and promotion of quantum computing in real world applications. And so, Dr. Monroe, congratulations on the quantum computing user facility at Duke. And I want to see how these partnerships work. But there's a real world application that we've been dealing with this past couple weeks on cybersecurity and how we might be able to collaborate between research institutions and the private sector and use quantum computing to maybe prevent some of the kinds of things that we're seeing, particularly when we're dealing with 20th century technology that hasn't moved into the 21st century. And I don't know if the committee has dealt with this earlier. I was in another committee meeting, but I'd love to hear from you about how quantum computing might help us with cybersecurity.
Thank you for the question, Congresswoman. So indeed, the known killer application of quantum computers is code breaking, cracking the most popular data encryption schemes we have. It looks like that application is one of the hardest out there. We need much bigger machines to do that. That said, we also are. This has been said before. We're at such an early stage in the game. We know we can shrink the problem. We can make it more efficient through software by being more clever on how we structure not only the instructions that we run the quantum computer, but the quantum computer itself, how we control it. And this is why at Duke, for instance, we're collaborating we're starting a very large collaboration with the colleagues you mentioned at NC State, and they're experts in computer architecture. We make machines, and this is sort of a marriage that we really like the direction of that. Now, making code breaking problems easier is something that won't happen in isolation, won't happen by me, or won't happen by somebody that doesn't have a machine. So I think they have to work in unison. And at IonQ, we've worked closely with IBM. IBM also writes software that supports our system, the expression of our particular hardware. And IBM, I think, has really taken a lead at educating the public on using systems. They were the first to put their system on the cloud, and we've sort of followed a few years later. So it's a wonderful ecosystem down here in North Carolina, but also at the company IonQ, which is a Duke, Maryland startup up inside the Beltway in Washington. They're very close to the National Security Agency, and we understand that community's needs in this field. So it's I don't know what else to say. It's a very exciting time for the field. We'll take problems anywhere they come from, but security is a big one. And I think one last comment. What's not mentioned so much is the energy grid. That's a huge logistics problem. And I was horrified to find out that apparently, I think the way energy is coordinated across the country, it's not done very smartly. It's not my field. I shouldn't comment on that, but we do know that's one of the most vexing optimization problems we have. And the news in the last few weeks, especially here in North Carolina, is that, boy, it'd be nice if we made that a little smarter in the future. I'm not sure exactly how quantum will play a role there, but if it's an optimization problem, we want to take a crack at it.
Well, you anticipated my second question, and that is how open are, some of our big energy companies to your help?
Well, at IonQ, we are, we're not a company that can afford to talk to 50 different companies in parallel, but we do have conversations with a few energy companies that have teams on the ground that are ready. They want to deploy quantum for their uses. These could be oil and gas, or related to big pharma, or developing new fuels. It is a researchy time in the field right now, but they're very open to working with companies like ours, like IBM, and so forth, and going into the future. So, in terms of the energy grid, that's definitely not my area of expertise. So thank you.
Thank you, Mr. Chair. I've exceeded my time, and I yield back.
Dr. Foster is next.
Thank you, and thanks to all of our witnesses here. Well, first off, for those of you who don't know me, I'm Congress's PhD physicist and also the Congress's AI programmer, although I only have really dabbled in TensorFlow recently. The question I had was a more general one about where you see this whole field is going of advanced computing. It seems to me it's likely to fragment. That traditionally we've had a whole big line of megaflops, big floating point pipelines for local partial differential equations, and that will continue for all the usual reasons, from weather maps to nuclear weapons and everything in between. And so that will continue, perhaps with an overlay of AI to do the grid scale optimization on the fly, but largely just a similar thing. And then if you look at what's happening in AI, the state-of-the-art AI engines are not in the federal realm anymore. They are, if you're just high-speed execution of GPT-3 and other AI interesting algorithms, the best engines are from places like Google for that. And I don't believe that the federal government is likely to be able to keep up with that industry will continue to pull ahead. In that case, the federal investment will largely be in paying for university groups to have access to these very advanced AI engines. And that's probably as ambitious as we should be in that front. And then, farther down the chain of I guess narrower calculation widths, you have things like neuromorphic engines, which may end up as not floating point or even low precision integer, but single bit computing engines for neuromorphic thing. And so those will be experimental for a while and may or may not become really important. And so from a federal point of view, we have to decide where to put, there's a bipartisan agreement that we should something like double the federal budgets. But we have to understand, whether to write a check for a big new initiative wholly in National Science Foundation, whether we should sort of scale up all of the existing enterprises and then see what they're able to produce in a few years. And the big part of that decision is whether we think we have to, what the mixture of small research and big facilities is going to be. Because that, anyway, so I'd be, I guess, Steve, we can start with you and what you see as DOE's role in that.
Well, clearly, Bill, our programs are really intended to advance the state of the art in scientific computing writ large, and so that essentially encompasses all of the technology paths that you just outlined. I mentioned earlier that the sort of the next obvious move post exascale is to look at heterogeneous computing systems, where in addition to GPUs, one could have neuromorphic chips and other computational technologies. And those types of machines would provide avenues to solve essentially new problems. But also, I think continued investment in quantum computing is going to be necessary. I do see a separation between sort of the classical Turing type computation and quantum computation. And so there may be, that may eventually divide, there may be a parting of the roads there. But at least at this stage in time, I think we need to really look at the diverse portfolio of technologies and not foreclose any options.
Yeah. Well, are there areas where you sort of believe will not be able to compete with industry? I think, as I mentioned, specifically of AI, are there areas there where it's clear already that the government is not going to be leading?
Well, so there are certainly AI applications that are going to be dominated by the high-tech companies, Google's and so on. The one area, though, that I don't see Google moving into is there is, with the advent of the exascale machines and the type of GPUs they have, they are actually the most powerful AI engines that exist. And this very, very high end of AI is something that I think is going to still be the domain of the leadership computing class facilities. You may disagree, but I mean, I think
I'd be interested because there's a different narrative coming out of Silicon Valley, and a lot of worry that small startups in AI simply can't compete because they do not have access to Google's and so on, Amazon's big AI engines.
Yes.
Does anyone else have, Georgia? Or?
Yes, I would like to add a couple of data points to make the case of why the supercomputers and exascale computers will actually be the powerful AI engines. And I would like to draw these experiences from the exascale computing project, and particularly the one that was mentioned earlier to support cancer. When we started that effort, the specific application we were focusing was not a traditional application that anybody would have thought about supercomputers, but it was a challenge application for us to start building deep learning frameworks to prepare frontier and for the scientific community. Well, in the process, we actually faced the philosophical debate: do you fit hardware to algorithms, or do you build algorithms, modify algorithms to fit hardware? Typically, we think of, I have a specific application, I will prepare a certain type of hardware to fit that particular application. Well, in the case of the supercomputer and cancer, we had to do the opposite. And what we discovered in the end is that for this particular application, by modifying the algorithm to make the most of the supercomputer, we exceeded performance, state-of-the-art performance. So that opened a completely new way of thinking about using supercomputers for applications that traditionally were not thought of that type. The second example I would like to give was the very recent Gordon Bell Award for the COVID-19 pandemic that brought together large-scale modeling and simulation of the complete envelope, viral envelope of 305 million atoms. But there was an AI workflow to accelerate that modeling and simulation. So that coupling of AI and modeling and simulation that was only possible on Summit. So I do believe that we see plenty of examples out there to support that these general purpose machines will be able to deliver a lot, even in the AI space.
All right, fascinating discussion. I've exceeded my time, so I guess I have to yield back.
Thank you, everyone. Before we bring the hearing to a close, I want to thank our witnesses for testifying before the committee today. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may ask of the witnesses. The witnesses are excused and the hearing is now adjourned. Thank you all. Have a good day.